In the previous class, I have introduced you basic of root locus. Today, we will look more into root locus and to get more understanding on the importance of root locus and the theory of root locus. Hopefully, today you will get more understanding on this, because root locus is important. Root locus will be used also in chapter 2 for controller design. That's why this is important. And in the final exam, there will be one question, one full question related on root locus. So let's discuss what is a root locus. Again, as I mentioned, I have uploaded the slide. So I hope you have, hope the slide is with you now, so that we can do, you can look into the slide and also do some examples, and also to take some notes. Because if you see the slide, most of the slide are, maybe not most, but half of the slide are empty, which will be given, we will discuss during the lecture. Okay, let's see this block diagram. This is a common block diagram, a closed loop system where we have GS is the transfer function. Normally we call GS as the forward transfer function, GS. Okay. And K is a gain. Okay. Sometimes we draw like this. We separate K and G. K, GS. Both are the same. Okay. Here they directly multiply K and G. And we have at the bottom, the feedback one is HS, feedback transfer function. If we have something like this, if we have a common, a standard closed loop transfer function, first we need to obtain open loop transfer function. Okay, usually we use short form OLTF, referring to open loop transfer function. Open loop transfer function in this case is obtained by taking just until here. Imagine that no feedback. Okay, imagine that the feedback is not connected. So open loop transfer function, if you are asked to obtain, is K, GS, multiply with HS. Okay, not only KGS, is KGS, HS. That is an open loop transfer function. And closed loop transfer function is obtained, of course, you learn block diagram reduction in the last semester, in the previous class, in the previous course. So it's actually KGS over 1 plus K GS HS. This is the transfer function for closed loop. So please please, you should be able to differentiate open loop transfer function and closed loop transfer function. We know that poles are important in control system, and they appear here. Pole is obtained by solving the denominator. If we want to get closed loop transfer function, the closed loop pole, then we have to look into the denominator here. They are important again because we can get the time response specification, and most importantly also is the stability. We know that in order to be stable, all poles must lie on the left half plane of S-plane. Okay? If only one on the right, then the system will be unstable. So poles are important. They determine stability. They also will give the time response specification. We get rise time, settling time, overshoot, under them, over them, everything, all through poles. If we check, the open loop poles are easy to be found. Okay, we can get open loop transfer function here, and then we get poles directly from here. It's actually, later we do one example, we can multiply and get the poles. And they do not change with the system gain. No K. K is only here. Okay, and because the pole is related to the denominator at the bottom, so K is not affected. So that is for open loop. However, for closed loop, they will be difficult to be obtained because we need to do this calculation, KGS 1 plus KGSHS, and will be difficult for higher order system. If second order, then easy, but become third order, fourth order, 10th order, it will be difficult. We need to do some calculation. Of course, MATLAB can do for us, but in order to do manually, it will be very important for a higher order system. But another thing which is more important, the closed loop poles change with the system gain. We can see that the gain here, K, appear in the denominator. Then K will affect the poles. For the closed loop transfer function, K will affect the pole. In contrast to open loop, in which K does not change the pole. So that is why root locus come in. Okay? Because the pole is changing with K. So now we want to see what happens if K changes. If I increase K, what happened to the pole? Okay? So we want to investigate. We want to have an approach to investigate what happened to right here. What happened to the poles, to the closed loop poles when K changes? Okay. So we want to have an approach to investigate what happened to the closed loop pole when K changes. We know K affect the poles. Okay. So that is important to see what happened to the pole. And this is obtained by having root locus. Root locus is actually a diagram. It is a root. Root refer to the pole. Locus mean how it moves when K change. Okay, let's do one example first to see the one that we just discussed. Let's take a system here, K, GS, HS, in which GS is here, this is GS, this is HS. Find open loop and closed loop, pole and zero. Okay, now write the open loop transfer function and closed loop transfer function. I want you to find open loop transfer function and closed loop transfer function. Do it now. Open loop transfer function and closed loop transfer function.
Doctor,
Yeah.
what is the value of gain? K.
No need again.
Oh, okay.
I just want you to find transfer function. No need to solve at this moment. Okay, we know that open loop transfer function is K, GS, HS. K, GS, HS equal to K, S plus 1, S plus 2, we continue S plus 3, S plus 4. This is closed loop transfer, open loop transfer function. Therefore, we can obtain the open loop zero and poles. That means referring to here. That's why K is not needed here. We can solve open loop pole. Open loop zeros is S equal to -1 and -3. That means we solve the numerator. Open loop poles, we can get S equal to 0, -2, -4. Okay, from here, from the denominator. Then let's find closed loop transfer function. Is K GS 1 plus K GS HS. So it will be more difficult, more calculation is needed. Is K S plus 1 over S plus 2, 1 plus K S plus 1, S plus 2, multiply with S plus 3, S plus 4. Okay, so you need to be fast in order to solve for closed loop transfer function. You need to do it many times I'm sure you did it in the previous course, but again, this should be faster. There is a pattern to do it. You should do it, you should try, you should practice. So if you solve, again, this show that closed loop transfer function is more difficult. It need more calculation. And if you solve, you will get K you get K as plus 1, S plus 4. At the bottom is quite long, S3, 6 plus K, S squared, 8 plus 4K, plus 3K. Okay, please do this later. So we can, from here, we can get the closed loop 0 as S minus 1 minus 4. Closed loop poles. However, the closed loop pole is affected by K. That's why one of your colleagues asked for the value of K. But it will depend on the value of K. When K change, the pole will also change. In contrast to open loop pole, which are not changed, which are fixed, not depend on K. So this proves that the K, the gain is important. It affects the pole, which are also important. And that's why we need root locus. Root locus give a graphical representation of the closed loop pole as K varies. We want to see what happened to the closed loop pole when K change from 0 to infinity. From 0, K from 0 to infinity. I will move on. So next, we want to draw a root locus. We want to have a graphical representation of the closed loop poles. The question is, can we draw a root locus for a higher order system? Higher order system means the pole, maybe 4, maybe 5, maybe 6, many poles. Can we draw a root locus? Okay. And in order to draw the root locus, we need the properties. We have to discuss today the properties of root locus, which will help us to sketch. We will not able to draw the exact root locus. We can only sketch. Okay. Later, we will use MATLAB to have the exact drawing of root locus. But in order to gain understanding, we want the student to be able to sketch the root locus for a higher order system. Let's start with by considering a closed loop system with a feedback HS. That means when we say, that means this one, a normal one, KGS HS. The one that we normally use is a negative feedback. So the closed loop transfer function, of course, will be if I use T is the closed loop transfer function, is KGS 1 plus KGSHS. And if we solve the bottom one, we know that in order to get the pole, we have to solve the denominator. And if we take 1 plus KGSHS, denominator, and we equate to 0, that means we want to solve the polynomial in order to get the poles. And this equation, if we equate to 0, is called characteristic equation. Okay. So when people say characteristic equation, mean they equate the denominator equal to 0. And solving the characteristic equation will give the system poles. So I will write again here, 1 plus K GSHS equal to 0 is the characteristic equation. Or if I bring 1 to the right, we have KGSHS, sorry, KGSHS. Equal to minus 1. We can imagine that if we have for minus 1, if I draw a graph, minus 1 is here, is on the real axis negative, minus 1. This is actually equal to the one that with magnitude 1, and also the angle. If we say angle, 180 degrees. So it can be also represented in polar form. Magnitude 1, angle 180 degrees, which represent minus 1. As we can represent in this form, therefore, we have two criteria. One magnitude, and the other one is angle criteria. Magnitude meaning that KGHS, the magnitude must be 1. Okay? Or we can rewrite in this form. Or I can solve for the value of K, in which K equal to 1 over GHS. Later we will see, we will use this formula in future in order to get or to calculate the value of the gain, K. So that is the first one, magnitude criteria. We also will have an angle criteria. That means the angle of KGHS must be 180 degrees. Or we can also take another round, plus 360. That means 540 degrees, and so on. It will be the same. And it can be summarized as 2K plus 1 multiplied with 180 degrees, in which K equal to 0, 1, 2, and so on. And it can be also negative, actually. Negative mean from here to here. Also the same go to the same angle, same direction. So it can be positive, negative. We start with the characteristic equation. We solve equal to -1. Then we say it can be represented in two ways, two approaches. And then we separate it into magnitude and also angle criteria. That means all closed loop poles must satisfy the magnitude and angle criteria. So when we get poles of the closed loop, that means they satisfy these two criteria, magnitude and angle criteria, because they come from the characteristic equation. And therefore, all points on the root locus, later we will draw a root locus. Root locus represent poles, must also satisfy both criteria. These are important criteria that is used to draw root locus, magnitude and also angle criteria. Let's do some testing to prove that the one that we just discussed is correct. Okay. Remember this one? We did this in the previous class. We have a transfer function of this. We have this transfer function, K GSHS K over SS plus 0. And we calculate manually actually. When K0, we get value, K5, we get pole, two poles, pole 1 and pole 2. Let's take when K equal to 5, K5, we know that the pole are minus 9.47 here, and also 0.53 minus 2 poles. If we use that pole, we put into the equation, it should be fulfilling the both criteria, magnitude and also angle criteria. Let's try KGHS when K equal to 5 and S 9.47 negative. So I put 5, 9.47 negative, minus 9.47 plus 10. Here I substitute S with the value of the pole. Okay, if we solve this, you will get -1, showing that this fulfill our main the properties, which KGHS equal to -1. If you substitute with minus 0.535, minus 0.53, minus 0.53 plus 10, you should also get -1. In fact, if you try to substitute all these value and K and also another pose, all give KGHS equal to -1. All closed loop poles must satisfy these properties. And later, these properties is divided into angle and also magnitude criteria. Any question at this moment? We move on by using the criteria, the properties of root locus. So that means if we are given a point on the S-plane, if we are given a point on the S-plane, we can test whether the point is a closed loop pole or not. Or if closed loop pole meaning is on the root locus. Okay. How can we test? We should test by checking whether they fulfill magnitude and angle criteria. It can be checked similar to the one that we did here. Okay, we take pole and we substitute into the equation. If it fulfill KGHS equal to -1, then they are closed loop pole. If not, they are not the closed loop poles. So the equation can be solved. Equation meaning KGHS can be solved by using the tested point. Tested point means the one that we want to test. The point that we want to test. This is one way. We also have another alternative in order to check, to test whether it is a closed loop pole or not, by testing both criteria. Angle criterion, that means the angle between the point and open loop poles and zeros. We will do an example later. Here meaning that angles of zeros minus angles of poles must be 180 degrees. In order to fulfill the angle criteria, angle of zeros, later I will show you what angle of zeros mean, minus angle of pole is 180 degrees. The other criteria is to find the distance. Here angle, magnitude refer to distance between the point means the tested point, and open loop poles and zeros. So we want to find the length, the angle, the distance between the point and the open loop poles and zeros. In order to apply these alternative techniques, we first need to check for the angle criterion. Why we start with the angle criterion? Because we do not have the value of K. If we solve for magnitude, then we need the value of K. Okay. So we start with angle criteria. We check whether it fulfills 180 degrees or not. If not, then we say, no, this is not a closed loop pole. If 180 degrees, then this is a closed loop pole. Then we proceed with the magnitude criteria in which we can obtain the value of K. Let's do one example. Examine whether the following point, here we have 2 points, is a closed loop pole of the system. Now I have a system. This is a unity feedback system. We want to check whether this point is a closed loop pole or not. Use both methods. We can use two methods in order to check, to examine this. Okay, let's do together. We will do both techniques. First, of course, it must fulfill KGHHS equal to -1 in order to be a closed loop pole. First, we substitute the value on the test KGHHS, meaning K S plus 3, S plus 4, S plus 1, S plus 2. We substitute the value, the one that we want to test. So K minus 2 plus J3 plus 3 minus 2 plus J3 plus 4 divided by minus 2 plus J3 plus 1 minus 2 plus J3 plus 2. Then we get K 1 plus J3, 2 plus J3 over minus 1 plus J3, J3. We already substitute the value, the tested point. Now we want to test. As I mentioned, first we have to check the angle criteria. Checking the angle criteria. Okay, how can we check the angle? How can we obtain the angle? First, K. K meaning it's a constant K. It's a value on the real axis on X, positive X. That means angle K here is 0 degrees. That's why we start with angle criteria, because K here does not contribute to angle, is 0. Plus, it is normal. We get, in order to get the angle, we get the angle of the numerator minus angle of denominator. 1 plus J3, you can imagine that it's like 1 here, J3 here. It's like a point here, 1 plus J3. So the angle that we consider is this angle. Angle from 0. That means I can get here is tangent inverse 3 over 1. Tangent on inverse 3. That is the second one. The third one plus tangent inverse 3 over 2 minus all zeros minus pole. Pole here, if minus 1 J3 meaning here, minus 1 J3, if we take this angle alpha, the angle that we are interested is theta. Okay, that means minus, I get alpha 180 degrees minus alpha minus tangent inverse 3. minus J3. J3 meaning on the y-axis is 90 degrees. If you solve, please do it later again, you will get the value as minus 70.5 degrees, which is not equal to 180 degrees. Therefore, this point is not a closed loop pole because it is not fulfilling the magnitude, the angle criteria, which should be 180 degrees. Any question?
Doctor, can you explain that 180 part, negative 180 degree?
Which one?
Minus 180 degree, minus tan inverse 3, that part.
This is just to show, to find the angle of this, angle of minus 1 plus J3. Minus 1 plus J3 is I draw here, minus 1 J3 is here. Minus 1 J3. So the one that you were asking is just this one. I want to find this angle. Theta. Theta is 180 degrees minus tangent inverse 3. That is the one. You okay?
Oh, yeah,
You
understood.
know, you use all the trigonometry, the one that you learned.
Yeah.
So minus 2 plus J3 is not a closed loop pole. I mentioned just now that another approach is to obtain angle of zeros. This is angle of zeros. Here referring to the angle of the numerator minus angle of pole. These are the angle of poles. So actually angle of zeros minus angle of poles. But later we will show in a graphical form. Angle of poles. So then, if it's not, then we stop. We don't have to to check for the magnitude criteria because it is already not fulfilling one of the criteria. Let's move on. Let's check B. Okay, we want to check S equal to minus 2 plus J set 2 over 2. Whether it is a closed loop pole or not. Again, we will do the same. Okay, GHSS, we insert K minus 2 plus J set 2 over 2 plus 3 minus 2 plus J set 2 over 2 plus 4 over minus minus 2 plus j plus 1 plus 2. Okay, then we solve and get the pole, the angle. For this case, if you continue to solve the angle, you will get the angle equal to 180 degrees. I want you to do later. Okay, use the same procedure. You will get the angle is 180 degrees. Okay. So once we get the angle 180 degrees, it fulfills one of the criteria. Then we proceed with the magnitude criteria, in which K GHS equal to 1. Or we can rewrite K equal to this. In which we can calculate for K. How can we calculate for K? It can be obtained by solving for the magnitude. Let's say this one. Let take one example. This one, we get minus become 1 plus j 2/2. Similarly, it is at this point 1 j squared 2/2, and the magnitude that we mentioned here, we consider is this one. This is the magnitude. Angle here, magnitude is this. Sorry, not straight. This is the magnitude. How can we find the magnitude? That means we can use Pythagoras. In order to get this one. So I've did it. We get for this one equal to 1.22. Magnitude here is 1.22. This is the first one. The second one is 2.12, referring to this. Then 1.22, the same. 2/2. If you solve, you get 0.33. So the second point that we want to test, which is minus 2 plus j 2/2, is a closed loop pole because they fulfill both criteria. First, the angle criteria, which is 180 degrees, and we can also find for K. In fact, if the angle criteria is fulfilled, normally we will able to get K. Okay, that means if the first one is fulfilled, then it's almost certain that it is a closed loop pole, but normally we will proceed to get the value of K that give that pole. Okay, this is the first technique, the first approach in which you substitute the value of S into the equation and then solve for pole and zeros. Another approach which is also actually similar, but this must be based on pole and zero. First, we need to plot the open loop pole and zeros. That means from here we can get open loop pole and zero. Open loop pole at -3 and -4. We're solving the numerator. And we have, sorry, sir, I made mistake. This should be a 0. We have pole at -1, -2, 0 at -3, and -4. We want to test at S plus J3. This is the tested point. We want to test whether this is a closed loop pole or not. Then we take the point here, -2, J3. The way here is to get the angle criteria in which angle of zeros minus angle of poles. Angle of zeros meaning this one. From here, from the point to the zero. This angle, theta 1, theta 2, theta 3, theta 4. This is what we meant by angle of zero. So angle of zero here, theta 1 plus theta 2. Theta 2 minus theta 3 plus theta 4. It must be 180 degrees in order to fulfill the angle criteria. And later you will check, you get 70.5 negative. You can find using trigonometry, tangent, cosine, sine to get the value. And later, this is not a closed loop pole, not a closed loop pole. Then we test for another one. Then we test for another one. I need to do this because to show how to get the magnitude. -1, -2, -3, -4. The other one is -2j square root 2/2. Again, we get theta 1, theta 2, theta 3, and theta 4. For this case, when you solve, you will get 180 degrees. That means this point, closed loop pole. Once we solve or fulfill the angle criteria, we need to solve for the magnitude criteria. For the second approach, the magnitude criteria is actually K is equal to the length, distance. This is symbol for product. We multiply all length of length of poles divided by we multiply all length of zeros. That means if I take this one as L1, you can use Pythagoras theorem in order to get L1, L2 here, L3, L4. That means is L3 multiply with L4 divided by L1, L2. Please do it. You get 0.33, similar to the first case, similar to the first approach. Again, this is another approach. This approach requires that we have the diagram, the plot of pole and zeros, and then from the plot, we use the point, the tested point that we want to examine. We get the angle to all pole and zeros. Then we use the angle criteria formula. And once it is fulfilling the angle criteria, then we move to check the magnitude criteria. This is obtained by taking the distance between the point that we want to test to all pole and all zeros. Then we apply the formula to get K, which is pole divided by zero. We multiply all distance to the poles divided by all distance to the zeros. In this case, we get 0.33, similar to the first case. Please try this at home. It was asked many times in the test. Perhaps it will be asked in the quiz also. It was also asked in the final exam, especially on the properties, angle and also magnitude criteria. This is another example I want you to test, to do as a homework. Please try this. You just substitute this value into KGSHS and show that it is equal to -1. Okay, in order to fulfill the criteria. Okay, the bottom is the answer. Yes, and K equal to 10. You need to also calculate for the K. Okay. I remember one test asked exactly the same. Of course, they changed the value of the transfer function and the point, but it asks the same. Check this point, whether it is on the root locus or not. This is another example. Check S equal to -9 to this transfer function. It is it's already mentioned that it is on the root locus, and the question want you to find the value of K when S equal to -9. Any question before we take a break?
No, doctor.
We take a 10-minute break. We will continue with the way to sketch root locus, a procedure to sketch a root locus. Shall we start?
Okay, Roti, okay.
Now we are going into to look into the root locus procedure in order for us to sketch a root locus. As I mentioned earlier, we will not able to draw the exact root locus, but here in the course, we would like to introduce the student how to sketch a root locus. In here, there are 9 rules to help us to sketch the root locus. Okay, the first 5 rules are the basic rules, but later number 6, 7, 8, and 9 is used to refine the refine the plotting. Number 9 specifically is very important in order to analyze the root locus. So we will involve sketching and then refining throughout 9 rules. Before that, before we start sketching, maybe rule number 0 here, we have to mark the open loop pole and zeros. The first task to be done is to mark. That means to use small circle and cross for pole and zeros. Remember, the one that we will consider is the open loop. So it will be easier for us. We start with open loop, then root locker will show us the closed loop poles. Okay, rule number 1. Rule number 1 refers to number of branches. Later I show you what branches mean. The number of branches equal to number of closed loop poles. And usually number of closed loop pole is similar to the open loop poles. So that is number of branches. So usually similar to number of open loop poles. Okay, number 2, symmetry. The root locus is symmetrical about the real axis. As this is a graphical representation, that graphic we will see is symmetry about real axis. But they are not necessarily symmetry about imaginary axis, only the real axis. Rule number 3. Rule number 3 refers to real axis segment. Real axis means x axis. On the real axis, for k greater than 0, the root locus exists to the left of an odd number of real axis, finite open loop pole, and all zeros. This might be difficult to understand. We will show, we will discuss this. I will show by a few examples. Let's move on. Now we want to see example of rule number 1 and rule number 2. If we refer back to the one that we discussed earlier, this is the system and this is the root locus. The system here has 2 poles because s to power of 2, second order. Second order means 2 poles. 2 poles, if we refer to rule number 1, 2 poles meaning they have number of branches 2. 2 branches. Because 2 poles. Branches here refer to this one. Let's say before that, rule number 0, I forgot. Rule number 0, we plot open loop pole and 0. So here it's actually, initially it was like this. Here s plus 10. S one over s plus 10. So the pole here is s0 and minus 10. So here the pole, see, 0 and minus 10. So first they plot the poles. We can see the root locker. Root locker later I will show must have arrow. So you can see arrow here, arrow, and here also has arrow. And later it go up. This one go down. We can imagine this one like this, and this one like this. This is what we meant by branches. 2 branches. Number 1, number 2. So it go from here to here, going down and going up. 2 branches. Later with 3 branches, 4 branches. It depends on the number of poles. The root locus, rule number 2, is symmetry about real axis. This is real axis. We can see that it is symmetry about real axis, but not on the imaginary axis. Only symmetry about real axis. That one rule number 2, number 1 and number 2. Let's discuss rule number 3. Rule number 3 mentioned that on the real axis, okay, before that, I want you to plot pole and 0 on this S plate. Plot pole and 0. Plot open loop pole and open loop 0. We have 2, 0 at minus 3, minus 4. We have 1 pole minus 1 and the other minus 2. Rule number 3 say that root locus exists to the left of an odd number. of real axis. Rule number 3 only applicable to the real axis. So when we want to invoke rule number 3, we only see the real axis here. So the way is to give number to all pole and zero. Let's say, let's start with number 1. This is number 1. We start from the left, from the right. Number 1, number 2, number 3, and number 4. 1, 2, 3, 4. All, either pole and zero, we add together. So root locus say that it exists to the left of odd number. Odd number, this is odd number. Odd number 1, number 3. They exist to the left. So there will be no root locus on the right of this. It exists to the left. This is root locus. No root locus here because it's because they refer to the right of odd number or even number, to the left of even number. It only exists to the left of odd number. So odd number here 3 we have here. No root locus here, no here, no here. Any question? Branches later. I want let concentrate rule number 3. Any question on rule number 3? Okay, let's try this to see whether you understand or not. Plot pole and zero. Then find the root locus on the real axis based on rule number 3. We have pole at 0, pole at -1, pole at -2, 0 at -3, pole at -4. So we give number 1, 2, 3, 4, 5. Now we want to plot the root locus on the real axis. Do we have root locus here? Yes or no? On the right of number 1. Do we have root locus?
No.
No, doctor.
No root locus. Here,
Yes.
A.
Yes.
Do we have at A?
Yes,
Yes.
doctor.
No.
We will have root locus because on the left of odd number. So here root locus. Here B, yes or no?
No. No.
No, because this is to the right. C,
Right.
region C, do we have root locus?
Uh, yes.
Yes or no?
Yes.
We have root locus because it is on the left of odd number. Number 3, we have to the left.
Okay.
D, yes, no.
No.
Not on D because it's on the right or on the left of even number or right of odd number. C, E, number region E.
Um. No. Not sure.
Left of odd number. Left mean, of course, we have root locus here. Left. This is the this is how we apply rule number 3. Any question? Okay, one of your friends say ask about branches. Branches is actually later you will see more detail, not a difficult part. Is actually number of arrow. Later is actually number of poles. Okay. If I remove this, if I erase this one, you can see clearly that it go up. This arrow, this is arrow, another arrow is from here to here. This one from here to here. Actually, we do not know whether it's going up or going down. Either this one going up or going down, that is not important. But the one that we interested is the number of branches. In this case, is 2. From here, it go to here. This one go here. 2 branches. Okay, once we obtain rule number 3, once we understand rule number 3, we move to rule number 4. Rule number 4, because rule number 3 here, we just plot the line. Okay, actually root locus with arrow. You see this one with arrow. Rule number 4 will help us to put the arrow, to put the direction of this. Okay, this one without direction. Rule number 4 will help us to put the direction. Rule number 4 say that the root locus begin at finite or infinite zero, infinite pole. Sorry, pole. Root locus start from poles. Later I explain infinite. Okay, imagine just finite and infinite pole at k equal to 0. Remember that root locus showing pole when k changes, increase from 0 to infinity. So root locus start from pole and end at finite and infinite zeros, or at k infinity. Rule number 4 deal with starting. Where it start, where it end, the root locus. Let's see this example. I plotted this using MATLAB. This is the transfer function. We have two pole here, 2, 0. From here, the root locus will start from pole. So root locus, then we will have an arrow from here, from pole, and also from here, from pole. We will need to put arrow. And it starts when K0. K0. Where it go, it will end at zeros. So go here, then it go up, going to 0. This one also going up, going down to 0. Here K infinity, here K infinity. Root locus start from pole, end at 0. It start when K0, it end when K infinity. That is all about rule number 4. That means now we can add the arrow here. Arrow here. Okay. So it start with pole. That means arrow going out from pole. From pole here. And at 0. This one going up, going from pole, also from pole. This one later, another rule will help us to solve this. But at this moment, you should know that it starts from pole. It will end at 0. This one not yet ending. This one also. This one. This one. Going out. End at 0 is always going into 0. That's why I show another one. This is the root locus, the exact root locus. You see, it starts from pole. You see the arrow here. This one also going out. And then it will end at 0. And it become a circle. This one go here and this one going down, 2 zeros. And we normally put K. K0, K0, K infinity, K infinity. Remember that the locus is actually the closed loop poles. All closed loop poles. Okay, imagine that many poles here. When K change, all poles. We will not able to calculate all poles, but root locus help us to draw the loci or the locus. Any question? before we move into another rule?
Doctor.
Yeah.
How the circle form again? I don't understand the circle.
No, this is uh, the circle is not a standard one. Okay, we will not able to. There is no rule determine whether this is circle or not.
Oh,
The rule that we will later look into also did not mention about circle. This is a special case, circle.
okay.
So if you have two pole, 2 0 at adjacent each other, then it becomes circle.
Okay, Doctor.
Okay?
Understand. Understand.
Okay. Any other question? I mentioned earlier, I mean maybe first lecture or second lecture, root locus is quite abstract. This is what I meant by abstract. Okay? It is graphical representation, but you should know what that means. You should remember that we start by discussing about closed loop poles. So root locus is actually showing closed loop pole when k changes from 0 to infinity. So we can see what happened to the system pole when we change k. Okay? You can see it changed. Sometimes it becomes unstable when we increase the value of k. We have done root 1 to 4, then we move to rule number 5. So before that, let's discuss, I mentioned I want to discuss finite and infinite. What that means. Let's take this example, k as s plus 1, s plus 2. We have 3 poles. How many zeros we have? How many zeros we have here? Anyone can have? How many zeros we have? 1, 2, 3,
One.
1 0. It is wrong.
Yeah, no zeros, no
No
zeros.
zeros.
So here
There's
no
no
zero.
S. Yeah,
Only
No
gain.
zero.
yeah, no.
3 pole, no zero. Okay. This pole are called finite pole. Finite means the one that we can calculate. We can see finite. Okay. From here we solve the denominator. We get as 0 minus 1 minus 2. But remember that we say root locus start at pole and at 0. Start at pole and at 0. But here no 0. Only 3 poles. So this is what we discuss. We want to discuss about 0. So in this case, if poles are more than zeros, the other is called infinite. So here we have infinite 0. In root locus, together finite and infinite will be equal to the number of poles. So here we have 3 infinite 0, infinite zeros. Okay, if let's say I have like this, We have 1, 0, 3 poles, and later we will have another 2 infinite zeros. So that total are 3 similar to the pole, so that we can, so that this can be, this is applicable. Root locus start at pole and at 0. The next question is, where are the infinite zero? If we say we have 2 or we have 3, where are they? Okay. So that is shown by, that is discussed in row number 5. Row number 5 will help us to locate the infinite zeros. Row number 5 will help us to locate the infinite zeros. They are actually at infinity. Okay, let's move into row number 5. Row number 5 discusses about behavior at infinity. It is related to infinite zeros, and sometimes we also have infinite poles, but most of the time only infinite zeros. The root locus approaches a straight line as asymptote, as the locus approaches infinity. We will have another term here, asymptote. Okay, let's see a few formula related to rule number 5. Before that, this rule is required or is applicable, is used when we have infinite fold or infinite zeros. Only if we have, if the number of poles not equal to 0, then we need rule number 5. If not, we can skip rule number 5. Before I proceed, as I mentioned, we have 9 rules. Not all rule is applicable to the system. It depends. Some rule is not applicable, are not applicable. We have to decide whether we want to, whether the rules need to be used or not. Okay? But basically, usually rule number 1 until rule number 5 are used in most cases. Okay, but when we do refining, then we may use or we may not use. But you have to decide based on the system given to you. First, number of asymptotes. Number of asymptote is number of, I use this as number of poles minus number of zeros. This is number of asymptotes. Okay. Next is real axis intercept. Normally we show by sigma. Sigma equal to total pole minus total zeros divided by number of poles minus number of zeros. And the angle theta is 2k plus 1 multiplied with pi here 180 degrees, divide by number of poles minus number of zeros. And k from 0, plus minus 1, plus minus 2, and so on. We have to remember the formula. Let's do one example for today. Last example for today. Sketch the root locus for the system using rule number 1 to rule number 5. Now we want to use rule number 1 until 5. First, plot the pole and 0. Now all I want you to plot pole and 0 on S plane. How many poles we have?
One pole.
4.
How many poles? How
Four.
many zeros?
104 poles.
1044.
Yes.
Now plot on S plane. We have pole at 0, minus 1, minus 2, minus 4, and minus 4. And we have 0 at minus 3. So we know that we will have 4 branches because 4 poles. Now use rule number 3 to plot the root locus on real axis. Give number 1, number 2, number 3, 4, 5. Now I want you all to plot root locus on the real axis. I think we need more time here as we are approaching 10 o'clock. I will propose to end the lecture. We will start tomorrow lecture by looking into this example. But this is important, summarizing rule number 1 to rule number 5. I will stop here. Any question?
No,